This is a quick video about energy, but from a purely problem-solving point of view. We're not interested in why energy is conserved or what symmetries that implies about the universe or even what energy is. Really, what we want to know is, in a basic introduction to solving conservation of energy problems, how do you use the formulas for kinetic and potential energies? So energy comes in kinetic, which is motion, and potential energy, which takes the form of gravity and position. There are other kinds, but we're not interested in them in this video. Let's say you have a box, and if I told you the box had a mass of 10 kilograms, that probably makes sense. And you probably assume that that's a fixed property of the box. That if the box has 10 kilograms now, you can move the box wherever you want. You can move it up, down. It will always have 10 kilograms worth of mass. Energy is the exact same way. If I tell you that a box has 1,000 joules worth of energy at any point, that box always has 1,000 joules worth of energy. It carries it with it wherever it goes. Now, energy can be potential or kinetic, so it might be distributed differently, but it'll always have 1,000. Let me explain what I mean. Let's say that all the energy was kinetic, right? That means that the box flies around because it has kinetic energy. Kinetic energy means it has speed, right? Well, what happens if I want to bring gravity into the picture? Well, I know that gravity pulls things down, so if I try to move up or down, likely I'm going to have to fight gravity, and gravity's going to enter this picture. If I have the box slide up an inclined plane, it gets to a certain height, let's say it gets to 5 meters up, its mass is still 10 kilograms, as you'd expect it to be, and we said before, the energy is still 1,000 joules. It's a property of the box, just like the mass. So what does this mean, though, since we assume the box slows down as it goes up the ramp? That means the kinetic energy is smaller than it was before. Well, if the kinetic energy is smaller than it was before, where's the rest of the energy? Potential energy. As the box slides up the ramp, it loses kinetic energy and gains potential energy. You could imagine the box sliding all the way up the ramp until eventually it comes to rest, and now it has no kinetic energy at all. It's stopped moving. All of the energy now, of the 1,000 joules, has to be in the form of potential energy. For this box, the kinetic energy and potential energy always add up to 1,000 joules. So at the beginning, it's pretty clear that you can say all the energy is kinetic, so the kinetic energy is 1,000, and at the end, all the energy is potential, so the potential energy is 1,000. In the middle, it's a little trickier, so we need to do a little math interlude. And if you recall, the formula for kinetic energy is 1/2 mv squared, and the formula for potential energy is mgh. So what do all these things mean? Well, in the kinetic energy formula, mass, m is mass, so that's that 10 kilograms for the box we were talking about earlier, and v is the velocity, or how fast the box goes. So if the box speeds up, that number gets bigger. If the box slows down, that number gets smaller. For potential energy, you've got the same term, mass, and then you've also got this g character. This g is the acceleration due to gravity at the surface of the Earth, and it's also sometimes called the gravitational field. Those two are the same thing, and for our purposes, it's just some constant that we have to multiply in order to get the right number for potential energy. So that's about 10. And then h, that's the height. So we'll read that off the graph as we go. So coming back to our example, we have energy is kinetic plus potential energy. Let's see what that looks like with the formulas written in. And for our box, those two put together are always 1,000. So for the box on the bottom, it's easy. The kinetic energy is 1,000 because all of the joules are kinetic, and I have 1,000 joules, so all kinetic energy is 1,000 joules. At the top, it's easy too because it's not moving. There's no kinetic energy, so all 1,000 joules have to be potential energy. Okay, if I want to look in the middle, now I can use my formulas. So I know that one thing that's true about the middle is that the height is 5 meters. So I can calculate potential energy is mgh. I can plug in the mass, which is 10, the g, which is 10, and the height, which is 5, and I get 500 joules. How do I get the kinetic energy? Well, I don't know the speed, so I can't use the formula, but I know that this box has 1,000 joules no matter what. If it's got 500 joules of potential energy, it must have another 500 joules of kinetic energy. That way the total is still 1,000 joules. If I wanted to calculate the speed, I could. Now I can use the kinetic energy formula. So 500 joules worth of kinetic energy equals 1/2 mv squared. I can plug in some numbers. and eventually I'll find that the speed is 10 meters per second. There's a more streamlined way to do all this, and that is just set up all the equations right from the get-go. Say that the energy is equal to the kinetic energy plus potential energy, write the general formulas, and state right from the beginning that the energy is 1,000 joules. Then you plug in whatever you have and solve for the thing that's left, which in this case is the speed. And notice I get the same result. Okay, hopefully this is a good basic primer into problems involving gravitational potential energy and kinetic energy.